This video we're going to talk about how we'll handle transient conduction with spatial effects. We'll start by talking about a plane wall, but we'll extend it to cylindrical coordinates as well. So consider figure 5.4 from your book, which shows a plane wall suddenly exposed to a convective boundary condition. And remember in video 5.1 to 5.3, we said that if the Biot number was much less than 1 and we gave a cutoff of 0.1, then we could assume that temperature was a function of time only, since the temperature didn't really change that much at any given time within the wall. And so we can then use the lumped capacitance method. However, if the B number is larger than 0.1, we cannot neglect the variation of temperature with position within the wall, and the lumped capacitance method will not work. So in our case, our governing equation would be the heat conduction equation. It's a plane wall, so we only consider heat transfer in the x direction. There's no heat generation, and because the wall was just exposed to convection, we have a transient problem. It's second order in the x direction and first order with respect to time, so we need two boundary conditions and one initial condition. Our first boundary condition is the symmetry condition. The slope dt dx at the center is 0, so there's no heat transfer at x equals 0. The second boundary condition is the convective condition at x equals L. The initial condition is that the temperature of the wall is at a uniform temperature Ti. And the next step is to non-dimensionalize some of our parameters. Non-dimensionalization of variables allows us to scale up analytically obtained results to real flow conditions. It allows us to avoid round-off errors due to manipulations with really big or really small numbers, and it lets us assess the importance of, or relative importance of terms within our model equations. So if we replace the temperature with the non-dimensionalized theta star in our governing equation, we see that the form looks a lot like what we had before. I encourage you to prove to yourself that this is what you get. Now let's look at our first boundary condition. Our first boundary condition doesn't appear to have simplified the math too much, so let's move on to the second boundary condition. This puts things in terms of our Biot number, which is calculated using the half thickness of the wall. And then finally, we non-dimensionalize our initial condition IC. So in order to solve this, we need to define the solution of this differential equation as the function of two functions. One function has to be a function of time and the other has to be a function of position. So if we perform our separation of variables, what we ultimately end up with is a series solution. So here's our solution. Remember that theta star is the ratio of T at some location x in time t minus T infinity, the temperature of the convective fluid, over the initial temperature minus T infinity. T is a function of x, and T is really what you're probably interested in here. So we have a series solution. What you see are some variables with an n subscript, so you sum it up for n equals 1, 2, 3, and so on to infinity. The more terms you include, the more work, but the more accurate your solution. And remember that we said that obtaining the solution involves defining theta star as a function of two functions. One of those functions would be a function of time, and the other would be a function of position. Well, the first term accounts for the time effect. The second term accounts for the spatial effect, how the temperature is dependent on the x coordinate. The Cn value is a constant which depends on the value of zeta, and zeta is the eigenvalue, which is just a constant that satisfies this equation. The subscript on that zeta indicates that it'll be different at every n value. N equals 1, 2, 3, and so forth. So if you look in your appendices in table 4b3, you'll have a value of zeta for n equals 1, 2, 3, and 4 for this equation. If you have additional values for n equals 5, 6, 7, and so forth, you'd improve your accuracy, but of course, each subsequent term has less and less of an effect. Notice that this table starts at some pretty low Biot numbers. Would you use this chart if you had transient conduction in a plane wall with symmetric boundary conditions? If your Biot number was 0.001 or 0.008, The answer is no. Remember your lumped capacitance method? That would be a much better way to go. If your Biot number is 0.1 or less, you could ignore spatial effects and you can use that much easier method of figuring out the temperature in your medium after a certain amount of time. So let's say that your Biot number is not less than 0.1 and you can ignore spatial effects. You can calculate your Biot number. Let's just say it's 80, for example, which is pretty high. And so we take our zeta 1, zeta 2, zeta 3, zeta 4, and plug it into our equation for theta star. You need to make sure that your calculator is in radians mode and not degrees when you plug that in. And then you use that calculated theta star to get get t at some location x and sometime t. And now, as you can see, that's a lot to plug into your calculator. And even with 4 terms, you still know that this is technically an infinite series. Can you get away with fewer terms to make the math easier without compromising accuracy that much? Well, it turns out that unless you're specifically interested only in the conduction really early on in the process, if a little time has passed, then only using the first term is pretty accurate. So if the dimensionless time constant T star, which is more commonly known as Fourier's number, is over 0.2, then you only need to calculate theta star using the first term. So we can get rid of the second, third, and fourth terms, and we're left with a much simpler expression. This only works if the Fourier number is greater than 0.2. And if it's not, you need to calculate using more terms to get an accurate expression. So if our Fourier number is greater than 0.2, you can calculate theta star using the first term of this expression, which means that you only need zeta 1. And this information is also found in table 5.1 in your book. This table is really nice because it also calculates C1 for you. So if you look at the footnote, you'll see how they calculate that Biot number. L is defined for a plane wall of thickness 2L that's subject to symmetrical convective boundary conditions. The exact same information can be found in graphical format. These are called the Heisler Charts, and a copy of the Heisler Charts that we'll use are available to you on the Canvas page. So remember how theta star is related to t as a function of x and t. So what we're going to do is we're going to define theta star in terms of 2 other ratios. You can see I haven't changed anything. The theta naught would just cancel out and give me theta over theta initial. So theta naught is defined as the midline temperature of the plane wall at some given time minus the temperature of the convective fluid. Theta initial is defined as the initial temperature minus the temperature of the convective fluid. This is one of our Heisler charts. It's applicable for transient conduction within a plane wall of thickness 2L, as shown in the top right picture. Notice that you can get theta over theta initial from this chart. And to read this chart, you need to calculate your 1 over your Biot number. Note that this is calculated with L, the half the thickness of the wall. And if you've done your calculations correctly, all the units should cancel out, and 1 over the Biot number should be dimensionless. Then you need to calculate your Fourier number, which is your dimensionless time. And once again, L is the half thickness of the plate. Also note that this is not a linear scale on the x-axis, so just be aware of that. All right, so we have the theta naught over the theta initial. So Heisler also gave us charts for theta over theta naught. And for this chart, you need the inverse of the Biot number and the dimensionless distance from the center. It just really depends on what you need to know. Sometimes you'll need to use a combination of charts to get the information that you need. Well, what if you wanted to define the amount of heat transfer from the plane wall to a fluid at any given time? Well, there's a Heisler chart for that as well. So the Q naught here is the maximum amount of heat that the wall can transfer to the fluid, or if the wall were cold, the maximum amount of heat that the fluid could transfer to the wall. And apply my first law of thermodynamics, or my energy balance, I see that Q naught is equal to the change in internal energy, which, assuming constant specific heats, is equal to m times specific heat times the temperature change. Note that I've written the temperature change so that I'll calculate a positive number if the wall is cooling down. If it were heating up, you could calculate a positive number just by flipping those. Let's see, then I put my mass in terms of density and volume, and I'm all ready to go to my Heisler chart. I could calculate Q at some time t if I've calculated the Biot number and the Biot number squared times the Fourier number, and then just read the Q over the Q naught off the chart. If you want, you can also directly calculate Q over Q naught by using this formula from your book, which some of you may prefer. Remember that you can get that zeta 1 value from the appendices in table B3 or table 5.1 in your book. There are also analytical solutions and Heisler charts available for long cylinders. So we have these solutions and charts for spheres as well, but we won't address them here. We're indicating that this is for a long or infinite cylinder because that indicates that we'll only consider temperature gradients in the radial direction, not the z direction along the length. If we had a shorter cylinder, we'd have to go back to the drawing board, get our differential equation for the heat conduction equation, and we'd have to get a temperature distribution as R, Z, and T. And that kind of problem is just outside the scope of this class. So let's tackle the analytical solutions first. We're only going to talk about solutions for the Fourier number being greater than 0.2 here. So you can see that if you have a long cylinder, you get an expression for theta star. You can also get an expression for Q over Q naught. Take a second to just digest that. Looking at the expression for theta star, which is defined the same way as we defined it for a plane wall, except this time we're using the radius instead of x. The first term in theta star accounts for the time effect. The second term accounts for the temperature dependence on the radial position. Notice that there's a Bessel function of the first kind. Don't stress about that one. There's a table we're going to use for this one. C1 is defined here. The only term I might be wondering about is the zeta term. Well, we can go back to table 5.1 and pull off the values for zeta at our given Biot number. Notice how they calculate the Biot number here. Be careful. Don't use R naught over 2, the one that's used in the lumped capacitance method. They tell you right there on the table how to calculate the Biot number, so follow what it tells you. So you get your Biot number and you read off the corresponding zeta 1 value. Now you're ready to look up what happens when you plug in that zeta 1 value to your Bessel functions of the first kind in your equations up there. That information is found in the appendices in table B4. You just go to your zeta 1 value, which is the x value in this table, and get the corresponding Bessel function to plug into your equations at the top. We also have Heisler charts that are applicable for a Fourier number greater than 0.2 for an infinite or long cylinder. Just like those Heisler charts for a plane wall, you can use a combination of temperature ratios to get the information that you want. The theta naught is defined as the temperature at the center minus the temperature of the convective fluid. Theta initial is defined as the initial temperature of your cylinder minus the temperature of your convective fluid. And another useful definition is Q naught, which is defined exactly the same as you defined it for a plane wall. You just have to be cognizant of your volume. We won't go through each of these charts, but they're on Canvas and they're analogous to the flat plate Heisler charts. So just be careful about your units and about calculating the Biot number with the radius, not the radius divided by 2. So I hope that was helpful. Thank you for watching. Let me know if you have any questions.